In the next problem, we are given a force field F, which is equal to the vector function whose coordinates are x and y squared. Now we want to know the amount of work done by this force field in moving a particle from the point 0, 0 to 1, 1 and then to the point 1, 0 along the line segments adjoining the points. So take note that the line segment connecting the points 0, 0 and 1, 1 lies on the line given by y equals x. And the line segment connecting 1, 1 and 1, 0 lies on the line x equals 1. So what we want to do is to decompose the path of motion into two line segments. So first, let C be the path of motion. Now we want to write C as the union of two curves C1 and C2, where in particular, C1 is the portion of the line y equals x from the point 0, 0 to 1, 1, and C2 is the portion of the vertical line from the point 1, 1 to 1, 0. Now let us look at this illustration. So we have here the line segment from 0, 0 to 1, 1, and this line segment is called the curve C1. Now the line segment from 1, 1 to 1, 0 is called the curve C2. So we see that C is the union of the curves C1 and C2. Now we want to parameterize the curves C1 and C2. Note that C1 is given by the equation y equals x. So we can set x to t and consequently y to t. So C1 can be parameterized by r sub 1 given by the vector function whose coordinates are t and t. And here t runs from 0 to 1. On the other hand, C2 is the portion of the vertical line x equals 1 from the point 1, 1 to 1, 0. So this can be represented by the vector 1, t. Note that here, t sweeps the interval from 0 to 1. But as t sweeps this interval, note that it starts from 1 instead of 0. Now, the line integral of f along C can be decomposed into a sum of two line integrals, namely the line integral of f along C1 and the line integral of f along C2. So all we need to do now is to compute these two line integrals and add the results. So let us start with the first line integral. So we are given f to be the vector function whose coordinates are x and y squared, and the curve C1 is parameterized by r1, which is the vector function whose coordinates are t and t. Now we plug in t to x and t to y, and so we obtain t squared. This is f evaluated at r1. Now what is the derivative of r1? It is the vector whose coordinates are 1, 1. So f r1 dotted with r1 prime is the vector t squared dotted with 1, 1. And so let's multiply t with 1, we get t, and t squared by 1, we get t squared. Now all we need to do is to integrate t plus t squared over the integral 0, 1. And so we have this definite integral here, and integrating t, we get t squared over 2. Integrating t squared, we get t cubed over 3. Now we plug in 1 to t and 0 to t. And so we will have 1/2 plus 1/3. And when we plug in 0 here in this sum, we get 0. So this line integral is equal to 1/2 plus 1/3, which is equal to 5 over 6. So the line integral of f along C1 is equal to 5 over 6. Now for the second line integral, we have again f equal to the vector function whose coordinates are x, y squared, and the second curve, C2, is represented by the parametric curve r sub 2, which is given by the vector function whose coordinates are 1, t. Now, f evaluated at r sub 2 is 1 t squared, and the derivative of r sub 2 is 0, 1. And so the dot product of f evaluated at r2 and r sub 2 prime is the vector 1 t squared dotted with the vector 0, 1. And so performing the dot product, we get 1 times 0 plus t squared times 1, which is equal to t squared. Now, let us integrate t squared from 1 to 0. The integral of t squared is t cubed over 3, and we evaluate this at 1 and 0. So plugging in 0, we get 0 over 3, which is 0, minus, let us plug in 1, we get 1/3. So this line integral here is equal to negative 1/3. So now all we need to do is to add the two line integrals. So recall that previously we computed for the line integral of f over c1, and that is 5 over 6, and the line integral of f over c2 is negative 1/3. And so performing this difference, we get 1/2. And so the work done by our force field F in moving a particle along this curve is given by 1/2.